Okay, let's move on to chapter 3.2, modeling gas. So you may have learned about ideal gas law, but then in our IB physics, this chapter, it will be something more about ideal gas law, of course, including its calculation, but also something more. So we will see how it goes. So right now, what I want you to do is try to read the first page and the second half page of this chapter in the textbook. You may want to pause the video now and we'll go through some key concepts. Okay, so the first thing that you should find is apparently the word Avogadro constant, and it is the number itself you can find equals to 6.02 times 10 to the power of 23. And if you have learned about chemistry in IGCSE, of course, I'm pretty sure you have learned about it also. But if you don't, that is totally fine. The idea is very simple. Let me give you an example. If you go to the shop to buy flowers for I don't know who, but then say you buy flowers, you may tell the shopkeeper that, oh, I want 12 flowers. Alternatively, you can also say 1,000 because simply this is equivalent, right? Mathematically equivalent to each other. Or if you want to say, oh, I want to buy 36 flowers, then that will equivalent to 3 dozens of flowers apparently. So it's the calculation itself is very simple. So here is the same idea, because when you talk about, for example, in this balloon, how many air exactly, like air in terms of particles, number of particles exactly inside, is very hard to say that. So instead of saying the exact number, we probably would say, oh, maybe there are 4 mole of gas particle inside, something like that. So when we do the calculation, we can convert from one to each other between them. And so the way you can see is the equation down here. But I would say I don't think you should memorize or rely on this equation, because you can simply tell directly by the numbers itself. Because for example, when I say, oh, let's say I really got like 4 mole of particles, so I would say so 4 mole, how many particle exactly? Then the calculation is actually quite intuitive, because you definitely get more number than, like a greater number than 4. So what you do is 4 times the Avogadro constant in that case, and then you can get the actual number. Or let's say I get now 10 million of particle inside the balloon, and I ask you how many mole are inside. Then apparently what you want to do is get 10 million divide by the 6.02 times 10 to the power 23, and in that case you can get how many moles are there. I would rather say, when you look at this equation, it's still important, but then I would rather like to show you would want to pay attention to the notation. Alright, and then you can see other than NA, which apparently is the Avogadro constant, you can see another 2 letters are the small n, lowercase n, and the big N, the capitalized N. And each of them apparently represent 2 different things, while the small n represent how many moles are there, and the big N representing how the actual number of particles. So this is something that you may want to remember. Small n, number of mole, big N, number of particles, and the conversion is simply by multiplying or dividing the Avogadro constant. And so taking the one that we set as example, then 4 mole is a small n, and the one on the right is a big N, or 10 million is the big N, and after you calculate this, it will be the small n. Okay, so this will be very useful for your presentation and also your calculation, so that you don't mess it up later on. The other thing that you may find is called the atomic mass unit. Okay, this is the second part, where you will find the definition of 1U. Well, this is a new unit you may call. Like normally, when you talk about mass, you would refer to the SI unit, kg. But then now, since in the atomic level, the things if you try to use kg, that's gonna be quite difficult, because 1 kg is a lot to 1 particle. So that's why we invented this unit. And what we do is the scientists in the past took reference of the carbon-12. And that is, I think one reason was because it was quite abundant in the world. So you can find in a lot of places, including or your body, or simply when you do, not you, that the plants do photosynthesis. There are starch or glucose, and there are carbon inside. So you can kind of measure it easily, and you can use it as a reference. Just like the definition of 1 kg in the past were relying on a chunk of big metal in the laboratory around the world. In case you know about the 1 kg definition, it's been changed I think 2 years ago. But anyway, so here we use the mass of one atom of carbon times 1/12, and that is simply because if you know about carbon-12, which is the most available carbon in the world, it has 6 protons and 6 neutrons in the nucleus. And the reason why we want to use 1/12 is because when you try to divide 12, then you kind of get the mass of 1 proton and 1 neutron. And probably you have heard that proton and neutrons mass are more or less the same. So in that case, then we can get the mass of 1 proton and 1 neutron to be around 1 U. And if you refer to the data booklet, then you can see for proton and neutron, you can see it's really close to 1 U, but it's not exactly 1 U, right? You can see the neutron is slightly heavier, and that's something that we may discuss again in chapter 7. It's something to do with the binding energy itself. So if you try to think about, if you try to use the kg system, kilogram system, you can see it's quite silly, and you can't really like feel the idea of the mass itself, because it's gonna be like 10 to the power of -27. So that's why we adopt this new system for describing the mass in the atomic level. I'm pretty sure the chemistry will also use that as well. Okay, so this is the idea of atomic mass unit. So right now, what we will talk about is in the next page. There's another some key ideas or terminology you may want to look at is atomic mass and also molar mass. So when we talk about atomic mass in physics, usually it will be in U. For example, just now for carbon-12, then we can say the atomic mass is roughly 12 U. And by the way, if you wonder, so what about the electron? You can see electron is much more insignificant. It's about 1/1800 times for 1 electron comparing to 1 proton or neutron. So that's why you can basically ignore that. So the other thing that's I think is more important is called the molar mass. Ask yourself, what is a unit of molar mass? If you study chemistry, you should know. The unit of molar mass, right, you may want to write down somewhere, which is gram per mole, right? Or you can say G mole -1 like this, right? I would say the most tricky thing is G, which means using gram instead of kg. I think it's defined by the chemists, and apparently this does not follow the SI unit since we use kg, but then using this in fact is more intuitive, because for example for 1 CO2 it will be 44 gram per mole. That means if you have 1 mole, it will worth 44 gram. And the way that you calculate it is knowing that CO2 is making up by 1C and 2 of the oxygen, and 1C has a atomic mass of 12, while the oxygen each will have an atomic mass of 16, and since you have 2, so times 2, and when you add together you get 44. So this is how you can evaluate or calculate the molar mass. Once again, remember it is gram per mole. If you do kg per mole, then it will be off by 1000 times. Okay, and lastly, there is a definition here where you can try to take a look, and it's actually quite obvious, but then try to take a look. 1 mole of substance is defined as the quantity of whatever substance that contains the number of particles that equal to Avogadro constant. So what it means is you may have 1 mole of anything. So for example, 1 mole of electron, then we're talking about electron containing numbers of particle or electron equal to the Avogadro constant. At the same time, you can also see a definition for molar mass, which I think this one is easy. Mass in gram for 1 mole. Okay, so right now, if you're okay with this, then again, you can see there's an equation, but then I don't feel it is necessary to memorize as long as you know about the unit. So using dimensional analysis, that means checking the units, will be quite useful later on. So right now we have 3 examples in your question set. So you may want to do it right now and we'll check the answer. And by the way, here is a meme for you. Okay, so let's take a look at the question here. There's actually one more question right here that I would like you to write down, which is the unit of molar mass again. And the answer is gram per mole. Again, it's gram, not kg. Okay, let's take a look at the first example and to see if you get the answers right. So it asks you the number of atoms. So it would be the best if you can write the symbol, the correct symbol next to it. So that should be the big N of 1 kg of gold. Okay, so in this case, you may want to be careful to look at this symbol, and you need to understand this. So 197 and 79, how do you obtain useful information from here is that the 197 representing how many proton plus neutron, right? And while the one below is how many proton only, because number of proton is kind of a little bit more important than the number of neutron to determine its element. So as long as it is 79, it must be gold in that case. You should have learned it in physics or chemistry in IGCSE also. But anyway, so since you know the total number of proton and neutron is 197, which is also the mass number, then that also means it is 197 gram per mole. Okay, so between the actual number and you also get mass, and you want to find well, you also have gram per mole, then you can think about the unit, how we can determine it. So that this is actually 1000 gram. So I would say the first thing you want to do is to find how many mole are there first. So what you can do is you can think about, if you want to get mole, then you should have gram divide gram per mole, right? So if you look at the unit here, then eventually you get mole in +1 index. So that means you will have 1000 gram divide 197. Then you can get the number of mole, and then you use your calculator, which you find is about 5.08, I would say, of mole. And then what you do next is to find the actual number. So apparently, then you can find, say, N equal to the number of mole times the Avogadro constant, which is 6.02 times 10 to the power 27. So I will just use my answers from the calculator directly, and I will find 30. So maybe I can kind of make it more scientific notation. So it's 3.056. All right. I don't know how many SF I should take. Let's say this is 2. So let's just take 2 SF then. So 3.1 times 10 to the power of 24 in that case. So the unit is no unit, right? Because this is simply number of how many golds are there. Okay, gold atom, I should say. The next question is how many grams? So you want to find gram, and here you get 45 gram per mole, and contains the same number. This is quite interesting. Same number of molecules. So that means if you talk about the small n or sorry, big N or small n, both are the same. I mean, if you have the same number of mole, it will be same numbers of molecules also. So it depends on which one is more handy. Same as 8 gram of argon, which you can find is 40 gram per mole, right, from this one. So I would say the easiest way to do probably is using big N equals to big N maybe, alright, or small n equals to small n. It's really up to you. Maybe small n is easier. So how many mole of each of them is the same. So let's call it just simply N1 and N2. I don't bother with the symbol. So if you want to find the number of mole, then let's call this M, then M gram in that case. So you can find mole by gram divide gram per mole. Once again, you may want to check the unit. In this case, you get mole. And same for the other side, gram over gram per mole. So here I'm showing you the unit because I'm trying to teach you how to do it in a more confidence way, like confidence as in you know this is going to be correct. And I strongly recommend you to do that. But of course, writing the unit is not necessary. It's not mandatory in the exam itself during the intermediate steps. So for the scandium, we would have the unknown mass. So let's put it as M, and then the molar mass is 45. For argon, it is 40, and gram is 8 gram. So just simply solve this equation, and you should be able to find the answer, which should be 9 gram. Okay, 9 grams simply. Okay, so the last question in the example is it asks you about the number of water molecules in ordinary glass of water. Okay, very interesting. So in this case, apparently you have to make assumptions or choose a reasonable number of like what it means by an ordinary glass of water. So normally I would say for a glass of water, I think it should be around 500 ml. Or it really depends on the size of the glass itself, but let's say it's 500 ml. If you know about the density of water, be careful, this is volume. So you have to convert to mass first, but then luckily for water, the density is simply 1, so you can convert this to 500 gram simply. And so for water, you have to have the knowledge to understand this is H2O, which I'm sure you know. And for H2O, apparently H is 1, and there are 2 hydrogens, so times 2, plus oxygen, earlier we mentioned is 16, so that equals to 18, and you in this case 18 represent 18 gram per mole. Alright, so 1 mole worth 18 gram in that case. So for calculation, you want to calculate the number of water molecule, which is the big N. You want to find mole first, for sure. So in order to find mole, then again you would want to use gram divide gram per mole. Yeah, so you can find the mole number, and that will be 500 over 18, and then you will get, using your calculator, 27.78 mole roughly. And then further on you can find the actual number. I'll separate the two calculation. So the actual N, should equals to the number of mole, 27.78 times the Avogadro constant. I'm just trying to be lazy. I'll be using the actual number instead of these in my calculator. So times 6.02, and then you should find 167.2 in your calculator, and then you can keep the 10 to the power of 23. You don't have to enter this, right? This is a little trick for you, and then you can then shift the decimal point to this, so you can kind of run, because I take away the 0.2, right? So I can round it up already. This is actually run off anyway. So it will be 25 in that case. Again, there's no unit for this. Okay, so that is all for the calculation. It's very simple.